Hello and welcome back, everyone. So today in our first video, we're going to talk a little bit about recap of ridge regression and dive a little bit deeper into how to choose that regularization parameter lambda. That's going to be the focus of this video. And in the next video, we'll talk about this application of one common machine learning task called feature selection. So here I want to recap ridge and explore one other component that we didn't quite get to talk about on Monday. So, remember when we introduced this idea of ridge regression in our pre-lecture video for last time, we talked about overfitting tends to happen in regression models when the coefficients that are learned are very, very large. And one way of getting overfitting to happen is to use polynomial features with high degree polynomials, which in that case, you can learn a very complex polynomial function from the input data. But we also said this could happen if you just have a large number of features more generally. There's nothing special about polynomials. The more features you have in general, the more ability your model has to potentially overfit. So generally, more features can potentially lead to overfitting. And so we talked about one way of spotting this was by looking at the coefficients or the magnitude of the coefficients. Now, when we saw these like lines that are going up and down, that maybe is indicative of overfitting, we generally saw that the coefficients learned were quite large. Whereas when you have a more reasonable model, one that's a much smoother curve that doesn't bounce up and down all over the place, generally these coefficients learned are more reasonable in range and will be smaller. To give you a sense of scale, remember I showed you this demo, and let me scroll up. I showed you this demo of how when you overfit a model, as you increase the degree polynomial of features, you can learn more and more complex functions. And we saw that this bouncing up and down behavior might have been indicative of overfitting. And one way of quantitatively trying to find that is looking at the magnitude of the coefficients. And so in this second demo I showed just looking at the magnitude of the coefficients. I think I'd take the average magnitude. Just take the absolute value of each coefficient learned, average them up for all of the coefficients in that model, and I show this average magnitude as a function of the degree polynomial we're training. You can see when the degree is small, near 0 or 1, the coefficients are very reasonable. They might have the scale of 100 because prices are large numbers, so it's okay that they're around 100. But as you increase the degree, the magnitude of these coefficients blow up in magnitude, whereas in a 30-degree polynomial, we're talking about 10 to the 12th degree, magnitude of our coefficient. Those are huge numbers. And so, I'm recording this through Zoom a little bit. I'm not. So, when we see these large coefficients, we might know that we might be overfitting. And so we discussed a way of trying to counteract this overfitting, which was regularization. So particularly with regularization, we change our quality metric to not just minimize training error, but to also minimize some notion of magnitude, how large the coefficients are. And in particular for ridge regression, which we talked about on Monday, the measurement of the coefficients was this L2 norm. So let me draw this in red. L2. And just as a reminder, this notation here is defined as the sum from j equals 0 to d, if you're talking about a d-dimensional coefficients, of wj. So it's the sum of the squares of all the coefficients. This notation here is just fancy math notation to talk about the sum of. This notion of norms is a very common discussion in mathematics, and so they use this concise notation. When you see this notation, I'm talking about the L2 norm, also known as the sum of the squares. So I'm squaring all the coefficients, adding them up. And so we explored, well, okay, if I'm changing my quality metric, this will change which model I think is the best, or which predictor in a particular model is the best. So if I'm using this particular sum of squares, it's going to be in my coefficient magnitudes, it's going to change which coefficients minimize this sum. It's no longer the coefficients that just minimize RSS. It's the coefficients that minimize RSS plus this weighted magnitude, where we use lambda to control how much we want to penalize large coefficients. And so we discussed what happens as you change lambda. Lambda is a hyperparameter, or a value you choose as the modeler, that will affect which predictor is learned from your ML algorithm. If you make lambda low, near 0, it's saying you don't want to penalize large coefficient very much. And if you make lambda large, it's going to penalize more. And we talked about this spectrum, where you can control how much you want to penalize large coefficients, where this penalty happens because we change our quality metric. Now there's certain coefficients might have larger values in our quality metric because it's the sum of these two things. And so we discussed where if you make lambda 0, then you're just minimizing the residual sum of squares on the training error. And this is exactly the old problem we saw last week. We sometimes call this the least squares solution, normally just minimizing the sum of squares. We call this least squares, or ordinary least squares. Or ordinary least squares. And so if you set lambda to be 0, you're saying, I don't want to penalize coefficients at all. This just reduces to the problem we had last week of just trying to fit a linear model. And again, linear in terms of the features. You could still have this really complicated model learned if you're using features that are very complex, or polynomials. So in this case, when lambda is 0, the ridge regression model is just the same as the least squares. You're just going to learn the exact same set of coefficients. Now, what if you make lambda very large? So what if you make lambda something near infinity? Well, if you make lambda too large, then any non-zero coefficient is severely penalized. Meaning that and this is simplified without using limit notation stuff, but if I make lambda infinity, then if any of the coefficients are non-zero, then this cost of residual sum of squares plus infinity times the magnitude is going to be something close to infinity. It's going to be quite large. So if you set lambda too large, it's going to make the cost of models that have even regular or normal coefficients very, very high. And in that case, we're in this limit where lambda is very, very large. The only cost that's not infinity is when all of the coefficients are exactly zero. In that case, you're only going to be getting some non-infinite quality, or in a sense cost, when all of the coefficients are 0. Then you just get some, maybe bad training error, but that's still better than the cost of infinity. So if you make a lambda infinity, the most penalty you can imagine, then you must learn the 0 coefficient. All coefficients go down. And then in general, is lambda in between those two extremes, you get smaller magnitude than the least squares, but probably larger than 0. Again, this lambda's infinity is like the extreme case of like most you can penalize something. But in general, you will be able to learn something much better and kind of in between these extremes. And so what I want us to explore now is, how do we explore this trade-off? What's the right value of lambda? And so I want you to start by I want you to try this out. So this is listed as a poll everywhere slide, but I'm not going to actually have you submit anything poll everywhere for this. But I want you to try to help figure out what might we do here. How do I choose the right setting of lambda? What I want you to do is I want you to take a minute or two. I want you to actually pause this video and think through these options. And I want you to write down in your notes which one you think it is and why. So I want you to go ahead and pause the video, try this out, and then when you unpause, I'll continue with the explanation. Okay, so now you had a chance to think through this. Let's talk about how we choose this lambda. So I think that in all of these options, we can start eliminating ones that have to do with that might potentially overfit. So for example, we don't want to choose the lambda that minimizes training error, because then we're just going to choose the one that overfits the most. the one that minimizes the residual sum of squares would be something that's actually lambda is 0, because then we can let the model overfit as much as possible. We also saw in our discussions last time that you never want to pick the one that minimizes test error, because remember, that will bias your interpretation of the test results because you chose the model that did best on that. So we don't want to ever do something with the test set. So anytime that you see something with test sets, you know you're not going to select your model. It's just a way of you looking at how your model will do. Get a good estimate. Similarly, we don't want to pick something that we don't want to pick something that minimizes anything on the training set, because if we choose the lambda that minimizes training error, it's always going to be the one that's overfit. So lambda near. Okay. Now this leaves a couple other options. One's about validation sets, and then we have a couple other about the largest or smallest coefficient. In this case, I'm also going to rule out these ones about smallest and largest coefficient. Well, we talked about large coefficients being overfit and generally small coefficients being underfit, or maybe not overfit. Generally, you don't want to pick your model just based off the coefficients, because there's not like a one-to-one mapping from this coefficient means you have a good model. So in general, we want to pick our model based off performance, not just based off the qualities of the model, like particular coefficient. And so this really leaves down two choices that have to do with the validation set. Either pick the one that minimizes the residual sum of squares on the validation set, or pick the one that minimizes the residual sum of squares plus that ridge penalty, L2 norm. And I think between these two choices, it's kind of not clear which one you should use. Because, well, ideally we want the validation error, but also we're using this ridge model. So should we use the ridge quality metric? It turns out that you're going to pick the one that minimizes the validation error, and you will not pick the one that minimizes the validation error plus this lambda times the magnitude of the coefficients. Now, why is that? Why do we throw away the ridge penalty when choosing the right lambda? Note, the ridge penalty is all about the quality metric while training. It's a change to the quality metric to help us figure out which learned coefficients best optimize the quality metric. And we change the quality metric to stop the learned predictor from overfitting. But when choosing the right lambda, the level of the penalty, we don't really care about that ridge thing anymore. We don't care about penalizing coefficients. We want to find the right penalty that yields the best model. And to choose the best model, we use the validation set. And we want to find the one that minimizes the validation error. This is a bit confusing at first, so I have a couple slides to walk us through this. So when you're choosing the coefficients, for any particular setting of lambda, the ridge regression objective, the quality metric we use while training, is find the W that minimizes the training error plus this lambda times the magnitude of the coefficient. But and we talked about if lambda is too small, it will overfit the training set, and if lambda is too large, then it will force the coefficients to be near 0. Now, choosing the right level of lambda is we want to pick the one that will make us do well or do best on future data. This means we want to minimize error on our validation set to get a good sense of which one's going to be doing the best in the future. Now, we don't need to minimize the validation error plus the sum of coefficients because you can't overfit to the validation data. You never actually trained on it. So you're not worried about penalizing coefficients. You're not training on validation data. Remember this, a change in the quality metric was to change training. So we don't include this because it's not relevant. Another interpretation of this is that it doesn't really make sense to compare this RSS plus lambda times coefficient magnitudes for different settings of lambda, like lambda is 0.01 versus lambda being 2 million. Because in this sense, this kind of quality metric is in different units now. It's not just error, but it's error plus this lambda times stuff. So generally, it doesn't really make sense to compare those qualities to different models, but it does make sense compare the validation error. That's the same unit across all choices of lambda. So generally, the way model selection will work when you're trying to use a validation set is exactly like using something like a validation set or cross-validation. For every possible lambda, train a model using your quality metric, which in this case is controlled by lambda. For each setting of lambda, the predictor you'll learn will be different. And then we compute a validation error on that learned model using our validation set or cross-validation, whichever you choose. And then we track the lambda has the smallest validation error and then report that, as well as the test error it achieved. So we use this kind of search where we train using whatever quality metric we use, but we validate just using validation error. Okay? That's a very key distinction and one that you want to make sure that you understand well or ask questions about if this doesn't make sense. That's all I have for this video. In the next video, I want us to explore one particular application of using coefficients that we learn to try to look at this thing called feature selection.